It's my pleasure to talk to you this evening about the end of massive stars. Massive stars are more important for you and I than you may first appreciate. And that's because if massive stars did not evolve as they do, and if massive stars did not end as they do, then we would not be here. It's as simple as that. But let's begin tonight's lecture by looking at this beautiful nebula. This is the Tarantula Nebula, and it can be seen from the southern hemisphere. It's as significant in the southern hemisphere as the Orion Nebula in the heart of the Orion constellation is to us here in the northern hemisphere. If this nebula were as close to Earth as the Orion Nebula is to us, it would be so bright that it would cast shadows. But in fact, the Tarantula Nebula is not in our galaxy at all, as the Orion Nebula is. It's in a nearby galaxy. Let's zoom in and take a close look. This is a particularly interesting nebula because it's the site of one of the most active regions of ongoing star formation that we can view. And as I said, it's immensely luminous because of that activity. If it were any closer to us, it would really be a very dominant source of brightness in the night sky. The Tarantula Nebula is a favourite target of the students at my Chile School Observatory, where this image was taken. This is a picture of us huddled in the cold of the Chile Observatory. I was thrilled to be able to visit there last year again after rather a long break due to lockdown. It is a favourite target there for a good reason. It's because it's a beautiful object. But it's a significant object for our lecture tonight because of its recent history and its recent contribution to something very important that happened 36 years ago next month. What I've done now is to zoom out. This is still a very similar region of sky. The Tarantula Nebula is at the top of this slide. Still an image taken at my Chile School Observatory. Where the pink arrow is pointing is the site of a very exciting event that happened in February of 1987. I'm going to show you a before and an after image of that sort of region of sky. Apologies for the 1980s font there. But where that arrow is pointing is the site of what was, prior to 1987, a reasonably unremarkable star. And this is after that star underwent a supernova explosion. That star that the arrow is pointing to on the left ended its life with a bang. It underwent a supernova explosion, and I'm going to be addressing tonight how that point is reached and its significance for us as humans here on Earth. I can't overstate how exciting an event that was in 1987. I wasn't scientifically sentient at the time, but lots of other people were. And I want to share with you a fax, yes really, a fax, not an email, sent between two physicists, two neutrino physicists, trying to do astronomy with neutrinos around the time that happened. Neutrinos, by the way, are particles that are important in particle physics, but they're very, very slippery. It's very hard to detect them. But they've been conjectured for a long time to be very important actors in the supernova experience. So anyway, here is a message written by Sid Bloodman to Eugene Bayer. Sensational news. Supernova went off 4 to 7 days ago in the Large Magellanic Cloud. So the Large Magellanic Cloud is a galaxy nearby to the Milky Way that contains the Tarantula Nebula. So it's about 50 kiloparsecs away, so a modest distance. Now visible magnitude is 4 to 5. We'll reach maximum magnitude between -1 and 0 in about a week. Can you see it? This is what we have been waiting 350 years for. Anyone who thinks that a scientist is a brain on 2 legs is significantly misinformed. Without the passion and the excitement that come from engaging in the spectacular phenomena of the natural world, you don't necessarily get the drive to realize clever experiments that enable us to understand more about the natural world. This question, can you see it, is asking, can you see a signal in neutrinos? Forget seeing it in light. People in the southern hemisphere were excitedly observing it in the southern sky. But Sid is asking Eugene, can you see it in neutrinos? So Eugene Bayer works on a particle physics experiment, or worked on a particle physics experiment called Cameo Candy, and so he looked at the data. This is how you looked at data in the 1980s. And for anyone who can't quite see the trace of counts in line with the finger there, let me just zoom in. That spectacular explosion corresponded to a handful of counts in neutrinos, some of them having passed through the Earth en route to the neutrino detector. So this was an absolute triumph. It was utterly exciting, because had neutrinos been demonstrated to not be a player in supernova explosions, it would have been a big puzzle, and we would have understood a lot less about them than we had dared to think that we do. So let's park neutrinos for a moment and think about what will make a star go supernova. Will all stars go bang at the end of their lives? Well, absolutely not. And in fact, in the first lecture in this series, the one I gave before Christmas, which was entitled The End of Our Sun, that was really a proxy for the end of our sun and stars like our sun, stars with similar masses to that of our sun. They do not explode. They do not end with a bang. They expand, and they expand as red giants. The inner core collapses as a white dwarf. Comparatively quiescent compared with the massive star endings that I'm going to be speaking about tonight. So it's only if you've got a massive star that you stand a chance of exploding as a supernova. Massive here means something like 8 times the mass of our sun, or 10 times the mass of our sun, or larger still. The mass of a star is, as we'll see a little later in the lecture, turns out to be a very crucial property for determining the evolution and the ending of a star. Mass really calls the shots with stars. So let's consider the question, how rare are massive stars? Massive stars are really quite rare because they're less likely to form in the first place. Stars form, as I explained at the beginning of my previous lecture, by the collapse of gas clouds under the action of gravity. When the gas has collapsed and become very dense and even more dense and got hot enough for fusion to take place, once the process of nuclear fusion is underway, then you have a star. You will get a more massive star if you've got a more massive gas cloud that collapses to form a single star and doesn't fragment into a couple of stars or 3 or 4 stars. So getting a really massive star does require the initial conditions to be reasonably favourable. But they're certainly out there, and massive stars are a thing, but probably massive stars are at most 1% of all stars in the Milky Way galaxy. So 1% reduces our numbers of the supernova explosions that we're likely to get, but 1% isn't too bad. If you've got one of these really massive stars, then something else you need to know about it is that they live life fast and furious. The more massive a star is, the more brief a star's life is. It uses up all its fuel like the clappers, and then it's gone with a bang, as we'll see, but then it's gone. So the fact that even though you get 1% of stars being massive, the fact that they are visible only much more fleetingly than the much longer lasting lower mass stars, which are already more plentiful, means that you're less likely to see the activity and the excitement of a big, massive galaxy. These monster stars run out of fuel all too quickly on a timescale much faster than that taken for fusion to ignite in the lower mass stars. So their lifetimes are much more fleeting. That makes them much more rare. But nonetheless, when you look in any particular direction in the sky, and suppose we look at this beautiful globular cluster of stars, a cluster of stars that's almost like its own little galaxy within our galaxy. This one is called Omega Centaurus, also in the southern hemisphere, and indeed visible to the naked eye. You will find stars that are interestingly massive. But the conditions here in this cluster of stars is so different from our bit of the Milky Way that stars tend to evolve a little more differently anyway. The density of the stars themselves is so crowded that stars are only separate from one another by something like a light month. A light month is the distance that light travels in 1 month. And by astronomical standards, it's really pretty close. The nearest star to our nearest star, the Sun, is called Proxima Centauri, and that is 4 light years away. It's probably a good thing it's not vastly closer. It is certainly a good thing it is not merely 1 light month away. Life in a star in the centre of this globular cluster, Omega Centauri, would be pretty hectic. Here's another beautiful globular cluster. This one is called Messier 22. It's nearly 11,000 light years from Earth, and again, it's got a distribution of different masses of stars. Its spatial extent is comparable with the diameter of the full moon. One day, that Tarantula Nebula, that gas cloud, which is collapsing under gravity, that I showed you at the start of this lecture, will look a bit like this. Already the Tarantula Nebula is forming stars, but it's got a long journey to go on of hundreds of millions of years of forming more stars until it's stars everywhere, as we have in this particular cluster of stars, again, in our galaxy. So how do stars evolve, and how can we begin to understand their behaviour, and how can we begin to think in terms of how the mass of stars changes with time? Well, it turns out that the mass of a star strongly influences its temperature. The more mass that a star has, the more dense it will collapse to be, and so the more heat energy you can radiate. So how do we measure temperature in stars? It turns out this is pretty easy to do. Stars manifestly come in different colours. Now, I don't know how clear it is for you to see in this particular image that some stars are yellower than others, some stars are bluer than others. Turns out it's actually easier to see this if you defocus the telescope, and then you can see the colours a bit more clearly. It's exactly the same field of view, but stars come in different colours, and colour maps to temperature in a very specific way. Now, for those among you who are thinking, goodness, isn't colour a bit subjective? Well, it may be in the case of choosing which item of clothing goes with another item of clothing, but it's not the case in astronomy, because in astronomy, colour is measurable, it is quantifiable, and repeatedly so, and it tells us about physics. If you think of a star as a big ball of gas undergoing nuclear fusion, the colour that it shows itself to be arises from the spectrum of light that we get from it. And the temperature that that ball of fusing gas is at determines exactly where that appears on the spectrum, and hence what colour it turns out to be. All bodies radiate in this way. Now you may be thinking, well, hang on, the colours that we're looking at, corresponding to the clothes that we're wearing, surely that's to do with the colours that are radiating off the light bulbs according to the nature of the light bulb and according to the fabric that our clothes are made out of. Sure, I completely agree with that. But I'm talking about the radiation that a body gives off by virtue of its temperature. This is honestly the case for all bodies. Now, it's notable, isn't it, that when we put the lights out at night, we don't see anything. We don't see the objects in our bedrooms. Well, you would if you got a thermal infrared imaging camera, because they would be radiating at 20 degrees or whatever temperature our bedroom is set to. Which part of the spectrum an object radiates at depends on what its temperature is. And so colour gives us temperature, and depending on what we're talking about, we can totally tell what temperature it's at. If we're talking about steel, then a muted red colour will tell us that that steel is at about 600 degrees. If it's bright red, it's about 800 degrees. If it's orange, it's 900 degrees. If it's yellow, it's over 1,000 degrees. And if it's white, it's more like 1,300 degrees, if we're talking about steel. Now, in thermodynamics, when we talk about the radiation from a body because of the temperature that it's at, we tend to think in terms of what in thermodynamics is called a black body, a body that doesn't absorb or emit preferentially in terms of one particular colour. It's not to do with the light bulb that's irradiating it. It's all to do with temperature. If you ascribe a particular temperature to a black body, you've got a map for the shape of the spectrum of light that is emitted from it, and hence its colour. So here is an example of what is known in thermodynamics as the black body spectrum. And you can see that the spectrum shifts over a bit into the visible part of the spectrum, which is shown over here in pale grey, only when the temperature of that body gets hot enough. And so immediately we can tell stars are very hot because we see them in the optical waveband to which our eyes are sensitive. This is the view over my house about 45 hours ago. So I have an all-sky camera on the side of my house. I have a very tolerant husband, and you can perhaps even see already, certainly if I zoom in, that some of the stars are slightly different colours. Thankfully, stars are at temperatures where we can see them in the optical, and I hope that maybe you recognise this distribution of stars in the bottom as our beloved Orion constellation. And perhaps you can see the orange-red one in the top left corner, that's Betelgeuse, diametrically opposite which is Rigel, which is rather more blue in colour. Just that observation from an all-sky camera on the side of my house on a cold winter's night, giving us different colours for those two stars, immediately says they're at a different temperature. If we split up the light into a rainbow, into a spectrum, we can see that Betelgeuse, which was the orange one in the top left, has quite a bit of red light, whereas Rigel, the one opposite, has rather more blue-purple light. Rigel is distinctly hotter than Betelgeuse. So looking at stars' colours tells us about the temperature, and that tells us where they are in terms of their evolutionary state and what their mass is. So let's draw ourselves a temperature scale. So the coolest stars you will ever see are a couple of 1,000 degrees. And the reason why we have that minimum there is a star is only a star if the condensed gas cloud is sufficiently massive that it could collapse sufficiently under gravity, that the densities were high enough, that the temperatures were high enough for nuclear fusion reactions to take place. At much higher temperatures, we see much bluer stars. And so already we can probably work out what the distribution of temperatures is for the stars in this image, which incidentally is also of Omega Centauri, but imaged by the Hubble Space Telescope operated by NASA. So we can see that the blue ones are going to be a whole lot hotter than the red ones, and the white ones are somewhere in between. So as we look at this, if we now rearrange those stars, thanks to a very helpful visualization by NASA, not changing the spatial distribution at all, but just ordering them left-right in terms of colour, so bluest blue on the left and reddest red on the right, we can see that we've got something of a striking distribution already. The bluest stars, the hottest stars, spoiler alert, the most massive stars, are relatively few in number. There are truckloads of the white and yellow ones in the middle, and again the red ones on the extreme cool side are relatively few in number. So we've got temperature increasing from right to left, a somewhat unusual way round. But now let's build up this graph further and think about how the luminosity, that is to say the intrinsic brightness of a star, the rate at which it puts out energy every second, let's see what happens if we now order the stars vertically according to how luminous they are. So these are the axes that I'm going to be using. And when we do rearrange the stars, I hope that you'll see very clearly a distribution of stars with a diagonal stripe going all the way across, which is known as the main sequence of stars. It's where normally operating stars who are following the instruction manual and undergoing nuclear fusion are to be found. So remember that diagonal line, and remember luminosity going up. So let's go back to the distribution of stars that we had just sorted in colour now, which is equivalent to sorting in temperature, and let's allow that to play out. So the most luminous stars going to the top. Oh, look, all the blue ones are going to the top. And we've got a diagonal stripe down here corresponding to the main sequence of stars. So although this particular diagram is only for the stars in that image of a small region of the Omega Cen cluster, if our sun were to be included on this graph, it would be just in the white region on the main sequence just there. So if a star is on the main sequence, it's undergoing normal nuclear fusion. If we could wind the clock back and look at this graph for the Omega Cen cluster in the past, all you would see would be a single diagonal going from the bottom right up to the top left. But the stars that have deviated and drifted off this main sequence are those that are entering the ending of their lives to an extent. So, for example, in this top right corner here, so this is relatively cool stars, but really quite luminous, that already tells you that they've got to be really quite big stars, because you've got to have quite a lot of stuff if you're going to radiate lots and lots of luminosity, even though you're at a very low temperature. And those stars, at least some of the ones on the left, will correspond to the red giants that I spoke of in my previous lecture. Some of these other giant stars right at the top, but off the main sequence, are ones that have expanded because of changes within the centre of the star. So where a star falls on one of these diagrams tells us a lot about its temperature, its mass, and how old it must be. If you form one of these diagrams for just a single cluster in the sky, for example, Omega Centaurus, as has happened here, then all the stars you're looking at probably have very similar chemical composition because they formed from the same original cloud of gas. They collapsed at around the same time, so they're pretty much of the same age. So to an extent, one of these diagrams is as important for stellar astrophysics as the periodic table is for chemistry. Now, this diagram is known as the HR diagram. Now, don't think about HR as in human resources. I'm sure they have diagrams too, but this particular diagram is known as the HR diagram after Hertzsprung and Russell. Hertzsprung was Danish and Russell was American, and they independently established this behaviour of stars. The fact that you have this main sequence of stars here, and then giants which are doing rather funky things after the normal fusion processes have ended. So where you are on this luminosity track depends strongly on mass. When your Tarantula Nebula ultimately collapses into your cluster of stars, like a megacen, the more massive stars will be on the top left of this main sequence, and the lower mass stars will be further down, less luminous and lower temperatures. Now, stars do come in all shapes and forms, and I just want to illustrate this with the help of some figures by David Jarvis. So just to help calibrate sizes now, we're thinking about the diameters of stars. Over there on the left, we've got Jupiter. Jupiter is lovely, the stripy planet in our solar system that we all love because it rotates and because it's pretty and it's got stripes. If Jupiter had a bit more mass, it would be a star in its own right, but it hasn't got quite enough mass to collapse quite enough for the densities to be high enough, for the temperatures to be high enough, for fusion to take place. So it's a planet, it's not a star, but we've got a feeling for how big Jupiter is. Next along is a star called Wolf 359. Wolf 359 is just about a star. It's one up on Jupiter. But it's a red dwarf and it's very faint. And we can only see it because of its proximity to the Sun. It's something like the fifth nearest star away from the Sun, Proxima Centauri being the closest. It's only about 9 light years from Earth, whereas Proxima Centauri is 4 light years from Earth. You can see it in an amateur telescope if you point in the right direction and there aren't clouds in the way. Next up, we've got the Sun. Next up, we've got Sirius. So keep Sirius relative to the Sun in your mind's eye. And now let's rescale. Here's Sirius, now Pollux, now Arcturus, now Aldebaran, which you can see in the winter skies. Now keep Aldebaran in your mind's eye. Let's rescale. There's Rigel. Remember Rigel, kind of on the bottom right of the Orion Nebula, the Orion constellation? Now Antares, now Betelgeuse, the orange thing on the top left of Orion. Now let's rescale. And so on. Probably the most massive star we know about is VY Canis Majoris. And this is pretty massive. It's not the most massive star we know, but it's one of the largest in diameter. Its mass is about 17 times the mass of our Sun. And so the sizes of the stars that we can observe depend partly on the mass of a star, because the mass will tend to pull in and tend to cause more collapse. But equally, a star will then puff out if it's reached that stage in its evolution. Why will a star puff out? It's important to realise that the entire lifetime of a star is one long struggle, or rather one long series of struggles. There are two competing effects. One is gravity, as I've indicated. Now, if collapsing matter were completely cold and there was no viscosity and no anything other than gravity, it would collapse to a very dense point indeed. But the thermal energy increases and the density increases, and so you get temperatures which are high enough to cause fusion, as I've said. But when normal, and so offsetting that gravitational collapse is this thermal energy. And that takes two forms. One is the internal energy of the atoms and the ions that are whizzing around in the core of a star, and the other is the radiation pressure the momentum due to the photons themselves. If you've lost a lot of the fusion that's going on in the central core of a star, then you lose that sort of internal heat engine, and so you risk collapse. But if you have collapse, then you can reach higher densities again and higher temperatures. And even if you've used up all your hydrogen, things like helium can start undergoing fusion. More of that in just a moment. But hang on to the fact for now that this main sequence is where normal stars are normally fusing hydrogen. When they've used up all their hydrogen, they'll typically drift off the main sequence to the right and expand. They'll get bigger, and even if the temperature isn't that great, because helium will now be the atom that's predominantly fusing together to form carbon and other things, you will still get quite a lot of luminosity. So there'll be a bit of a cycle where you use up all the hydrogen and that heat source goes, yikes, there's a collapse. Then the density increases again and the temperature hikes up, and then helium can then undergo fusion. Now that's really the end of the game for low mass stars that I talked about in my previous lecture, the stars that go off and form red giants. But when you have more massive stars, the story isn't over. So I think I've already made this point that the HR diagram, the Hertzsprung-Russell diagram, for a single cluster of stars can be very instructive about the distribution of masses that you get, because they're all the same age, so they'll all have the same T0. They all started off the starting blocks at the same time. So what about this cyclic process, this fight between, this competition between gravity pulling things inwards and the thermal energy trying to offset that collapse? As I've already indicated, in low mass stars, once helium fusion has occurred, the mass isn't enough for the star to collapse enough, for the gravity to be enough to cause the temperatures to be high enough for anything else to fuse. As you go through heavier and heavier elements in the periodic table, it is harder and harder to get them to fuse together. In nuclear physics, if someone says it is harder for this to happen, that can usually be overcome by winding up the temperature. But in low mass stars, there's no mechanism for doing that. You can't attain the densities. So this is a slide from my previous lecture. Hydrogen burning is replaced by helium burning, and helium fusion, which within the core puffs up that outer shell, giving it a big diameter, a giant-sized diameter, lots of luminosity, but very low temperatures. When all the hydrogen is used up, we get that it's game over for a low-mass star. The central core will collapse and form a white dwarf in the way that I discussed in my lecture last time. But for high-mass stars, the game is very much not over when the helium has finished fusing, and when the hydrogen has first of all finished fusing, and then the helium has finished fusing. On the contrary, the pressures and the temperatures in that core that keeps wanting to collapse, but is regulated by the fact that when the temperatures increase because the star has collapsed, you start off a whole new fusion cycle again. For example, carbon fusion can begin if the star is sufficiently massive. And then the fusion of oxygen atoms can take place. These get harder and harder and require higher and higher temperatures, but if you can do it if you've got enough mass and you've used up all the preceding elements, so the collapse is really very, very intense. You can then start fusing together heavier elements still, such as neon and magnesium and silicon. And these will continue to power the star as a giant. In the process of all these different fusion cycles, first with hydrogen, then with helium, but then, uniquely for the case of high-mass stars, carbon, oxygen, neon, magnesium, silicon, sulfur as well, a process is taking place which we know in astrophysics as nucleosynthesis, the cookery, the synthesis of nuclei, the bits in the middle of the atoms. Now, there are four principal ways in which nucleosynthesis takes place in the universe. The first nucleosynthesis was shortly after the beginning of time, in the first few minutes after the Big Bang itself. And I've described that in my second ever Gresham lecture entitled Frozen in Time. So I'm not going to address that today. I've discussed the fact in my previous lecture on the end of low-mass stars like our Sun that nucleosynthesis of helium and carbon takes place in those stars. And that's great. The world needs carbon, kind of. Notice I didn't say CO2. For high-mass stars, the nucleosynthesis of heavier elements still, neon, magnesium, silicon, also takes place. But life couldn't exist with just those elements. And in fact, what we need is heavier elements still if life is going to exist. So these are the various different fusion processes that happen in different layers inside a massive star. The heaviest elements doing fusion closest in to the center of the star, where the temperatures are high enough for those nuclear reactions to take place. And you can see that I've just illustrated what those nuclear reactions are. But these nuclear reactions inside the fusion processes of massive stars are insufficient to populate all of the periodic table. So where do they come from? They come in the few seconds of the ignition of a supernova explosion. So you can get a lot of iron by just in the very end times of a high-mass star before it goes supernova. Now, and in the initial aftermath of a supernova explosion. And you can get heavier elements still. I put it to you that anyone who has got red blood cells coursing through their veins and their brain, and I trust that's all of us, would not exist if massive stars had not gone bang. Those of us wearing gold jewellery would not be wearing it if it had not been for supernova explosions. So hooray for supernovae. They may be rare, but they are crucial for life to exist. So it's important to appreciate that a supernova explosion happens not when a star is born, but when a star dies. Its fusion times are over. The collapse that when all the different elements that can fuse normally have collapsed, then there are various collisions and disintegrations, and a bit more energy is given off, and then the central core can collapse completely to a compact object. Much like as in the low-mass stars, the central core of a low-mass star will ultimately collapse into a white dwarf. The central core of a high-mass star will still collapse into a compact object, but a different kind of compact object, either a neutron star, for the lower mass examples of the high-mass stars, or a black hole in the case of the high-mass stars. And these supernova, regardless of whether the ultimate outcome is a neutron star or a black hole, these supernova explosions are responsible for putting the heavy elements into the interstellar medium, spewing out lots of gas, which then gets dense enough to form a nebula, much like the Tarantula Nebula I showed you at the start of my talk, and then ultimately to collapse again to form stars and planets like Earth. So, excitingly, a supernova does all those things which matter for life, but they can also give rise to a neutron star or a black hole. Black holes and neutron stars give rise to terribly exciting astrophysics. And I talk quite a bit about black holes in my third lecture as Gresham Professor, which was entitled The End of Matter, ? How frequent are supernovae? Well, on average, they're thought to be about 1 per century. Remember that handwritten facts in the context of the supernova that went off in 1987, we've been waiting 3.5 centuries for this. We've been waiting 350 years for this. We haven't had a supernova for a long time because it's only on average one per century, but they are stochastic. And we haven't had a really good supernova for, well, centuries. So the last one was in, the last really good one in our galaxy that was close enough to be observed and followed was in 1604. It's known as Keplers Supernova because Johannes Kepler studied it obsessively and made some really beautiful observations of it. This supernova was brighter than Jupiter, so it could easily be seen in the naked eye. And in fact, at its peak, it was brighter than any other star in the night sky. It was visible for over a year to the naked eye. And it spewed out quite a lot of mass, because when you get that core collapse of a supernova, quite a lot of mass is flung out in a big shock wave, a big explosive shock wave that in the presence of other gas clouds can cause compression and trigger the collapse of other gas clouds to form more new stars. Supernovae have a lot of exciting influence because they expand at speeds of thousands of kilometers per second. The kinetic energy of the gas exploded out of Kepler's supernova was something like 10 to the power of 44 joules. For all the 4.5 billion years that our sun has existed, it still hasn't radiated that much over its entire lifetime. Supernovae are seriously explosive. Just to help you calibrate that amount of energy, the energy use in the UK, which is more than it should be, in 1 year is only 10 to the power of 19 joules. Supernovae are seriously energetic events, and here is an image of what the remnant of that supernova explosion witnessed by Johannes Kepler actually looks like if you observe it today in X-rays. So this supernova took place in October of 1604. It was prior to the gunpowder plot by about a year. The monarch at the time was James VI of Scotland, James I of England, ultimately James VI of everywhere, I think. Gresham was still on its first professor of astronomy. I'm number 38. We are overdue for a really good galactic supernova. Here is the remnant of a supernova that exploded in 1054. It was observed by Chinese astronomers. It was observed by astronomers in New Mexico in the USA. All this debris is now known as the Crab Nebula. And the compact object at the heart of this supernova is a neutron star that actually rotates and spews out a whole lot of charged particles as it does so. It's a pulsar. It's a pretty exciting object. This guest star, I'm reliably informed, I don't speak Chinese, is described in this account here where it's highlighted in yellow. Their nomenclature was to describe it as a guest star. And there have been other stars that the earliest supernova witnessed and reported by the Chinese was in 185 AD. It's known as supernova 185. The brightest one was in 1006 AD. There were eyewitnesses in China, Japan, Iraq, Egypt, as well as Europe. There was then another famous one in 1572, which was studied by Tycho Brahe, and then the one in 1604, Kepler's one, the last serious one we had. And it was profoundly influential at the time because the idea that things exploded and changed outside of the solar system, beyond the moon, significantly challenged the Aristotelian idea that the cosmos was static and unchanging. Boy, do we know that the cosmos is anything but static and anything but unchanging these days. So although we haven't had a proper supernova in our galaxy since 1604, 36 years ago, there was a supernova in one of our nearest neighbours, in the Large Magellanic Cloud, which is one of the Milky Way's next-door neighbours. It's in the upper one of these two here. The Milky Way, much like its sibling almost, the Andromeda Galaxy, has quite a few satellite galaxies, little galaxies in their own right, self-gravitating, yet not unaware of the gravity of the Andromeda Galaxy or of the Milky Way Galaxy in addition. So it was in this galaxy here that's a neighbour of our home, the Milky Way, where the Tarantula Nebula is to be found and where this supernova exploded, as I said, in 1987. Australia's largest telescope, the Anglo-Australian Telescope, made lots of observations of it in 1987. Most telescopes in the world started pointing at it if they were far south enough to see it, and even to this day, their finding chart is still sellotaped to their fridge. Here's a more beautiful image which the Anglo-Australian Telescope made to commemorate 30 years since that particular supernova went bang. Well, I love studying things that change, and with my global JetWatch network of telescopes, I decided it would be fun to see if I could get a spectrum of that object and split it up into its light to see what elements were present. And sure enough, I could do that. Even with the relatively small size of my telescopes, you can see that I was able to split up its light into quite a lot of different elements. So a spectrum is where you split starlight into its constituent colours in much the same with a grating or a prism or something like that, in much the same way that raindrops in a cloud disperse sunlight. But we're looking at starlight or supernova light in this case. And you can see that even with my relatively small telescope, even 3.5 decades after the explosion, I can still detect iron and nitrogen and a few other bits and pieces. So it's good fun to watch it and to look for changes in how that supernova shell continues to expand. But I'm one of a number of people that is really looking forward to the next galactic supernova, the next supernova that is close to Earth and that we can follow with modern instrumentation. It is startling to realise that we haven't had a supernova in this galaxy since the invention of the telescope. It was terrific to have one in the neighbouring galaxy, in the Large Magellanic Cloud, just downhill from the Tarantula Nebula with supernova 1987A. But there's so many questions that supernova raised that we really want to get answers by studying for the next one. As you may know from my third lecture as Gresham Professor, I did talk quite a lot about black holes, which are the end point of the central compact core of a supernova of the most massive stars. And I love studying how black holes interact with matter. That motivated the network of telescopes that I set up around the world called the Global JetWatch, separated in longitude, so there's always one of them in darkness, precisely to be able to keep the watch going on variable phenomena, such as explosions, such as collisions, such as merging events, such as jets squirting out of the vicinity of black holes. There are many different facets to the astrophysics research that I can do because of the Global JetWatch, and one of them is preparing for the next galactic supernova explosion. We've planned and discussed protocols for what to do when that event happens. So that's a little description, that lecture there, of the Global JetWatch and the science that motivates it, how matter behaves in the vicinity of black holes. But this is the network of telescopes. There are 5 of them, as I say, separated in longitude around the planet, one at each end of Australia, one in rural southern India, one in South Africa, and one in Chile. And so between them, these telescopes can keep the watch going. I've studied quite a few nova explosions now with these telescopes, and we've had a ball. We've learnt a lot. Some of the ways in which those objects change and their spectra change with time is very rapid. It's timescales of less than an hour. And it's only if you can keep the watch going with such telescopes that you can hope to study and investigate in detail events on the timescales on which they actually happen. So I thought you might like to see how observations happen in practice. For our normal observations, everything happens really quite robotically. So we have a whole bunch of cameras which look out on the night sky. We have a narrow field finder scope. We have an all-sky camera updated since that one there. And all those cameras help us to be sure of what the surroundings are. Are there any clouds rocking up? Do we need to be careful to protect the optical equipment and the electronics from water? These are all the astronomical cameras appearing, and they take data in different ways according to the investigations that were taking place. The telescope acquires the target robotically. It takes an image, half a degree by half a degree, with a big imaging camera, which we then solve for astrometrically. In other words, we work out exactly where we're pointing in the sky, and then we line up, and then we can start doing our spectroscopy, which is up in the top left corner. That's aligning a target with an optical fibre that takes the light collected by the telescope down to the instrument called the spectrograph, which splits up the light. This is what happens when we know about the targets. But when a supernova goes bang, how do we know where to point the telescope? What is our warning going to be that a supernova explosion is about to be observable from Earth? Well, think back to the neutrinos. Neutrinos that I mentioned at the start of my talk herald by a few hours, probably according to different models, the onset of optical emission, optical light from a supernova explosion. So if we hear from our neutrino physics colleagues that they've got a sudden spike in a particular direction in the sky, we are going to start exploring. And the way in which we will explore is, so neutrino physicists are lovely and neutrinos are super, but they're really slippery, and you don't get directionality from wherever you point your telescope. So we could get an approximate position that's only good to, say, 10 degrees. At this point, we will be using the whole arsenal of cameras at our disposal in each observatories to try and find out the optical location of our telescopes with, for example, that narrow field finder scope. We can do a manual acquisition. Forget robotic acquisition, that's great for normal operations. But when we've got to manually steer the telescope to find an object that's suddenly brightening and getting brighter and brighter, we need to be able to act quickly. And we think we might be ready for that, and we're looking forward to it. These are some of the auxiliary cameras that will aid us in that endeavour. These are commensal cameras that support the main light collection of the telescopes. And here they are shown with some schoolgirls at my India telescope for scale. These mini telescopes, these commensal cameras, have a much wider field than the main telescope, and so they'll be capturing the light curves of wherever the proto-supernova and then the fully blown supernova is, wherever it is on the chip. So we'll capture the light curves at the same time as we get ourselves lined up to be able to do spectroscopy as well. So we're really looking forward to the next galactic supernova. It may not happen in the lifetime of anyone in this room, but if it does happen, I hope that we're ready, and I'll be delighted to tell you all about it. So big stars end with a bang. It's really important to appreciate this. A supernova explosion involves the most almighty release of energy over very rapid timescales, as you saw from the numbers in the context of Keplers Supernova, the one that went bang in 1604. So massive stars, as I've indicated, are important for life itself. And when they end, they do so not with a whimper, but most assuredly with a bang. Thank you very much.